Hello and welcome to week 4 of horizontal construction. This week the presentation corresponds to chapter 8, securing deep foundations, but we're also going to be looking at slurry wall construction. So let's go ahead and get started.
Deep foundations are used wherever shallow foundations cannot be used. Typically, the reason that a shallow foundation can't be used is because the topsoil is expansive, or the soil underneath has a low bearing capacity, or we have a deep frost line. They may also be used in buildings that house delicate instruments that are sensitive to the settlement of shallow foundations. Deep foundation elements comprise of piles and piers, and are similar to slender columns that are buried in the ground. They're prevented from buckling because they are confined by the soil. Piles and piers transfer the load of a building either to bedrock or to soil of a high bearing capacity by penetrating through the unsuitable soils. Piles are generally driven into the ground by pile drivers, except concrete piles, which can be cast on site into pre-drilled holes. Site-cast piles, however, are typically called piers or caissons. So let's first discuss some commonly used deep foundations. In this diagram, we see that both systems A and B are reinforced concrete grade beams that are supported by drilled piers. The only difference here is that A has a wood floor and B has a concrete reinforced floor. This type of construction is commonly used for light frame buildings where the upper soil strata is of low bearing capacity or the soil is expansive. System C is a reinforced concrete slab that is supported by piers and pier caps. This system is simply an alternative to the systems that you see in diagrams A and B. And System D is typically used for multi-story buildings. This is where you would have piles, pile caps, and then short columns as your foundation. Now, one of the tricks to deep foundations is supporting the earth around the foundation as you begin to excavate. This is far more complicated than with simple shallow foundations. So let's take a few moments and discuss the support systems for deep foundations. In the previous presentation, we discussed self-supporting sloped excavations. These excavations are fine if you're not restricted. However, in restricted areas, in other words, an area where buildings are adjoining to where you're trying to do your excavation, you're going to need some type of support. Typically, a cohesive soil that has a shallow vertical cut, we're talking about 5 feet or so in depth, you may not need any kind of a support system. However, typically you're going to be going a lot deeper than that, and deeper vertical cuts must be provided with a support system. A few of these systems are listed here, and I'd like to discuss them in detail. For excavated depths up to about 15 feet, sheet piles are used. Sheet piles are driven into the ground before you begin your excavation. They consist of individual steel sections that interlock with each other on both sides. These sheet piles form a continuous barrier to hold back the earth. Structurally, they function as a cantilever, and therefore they must be buried into the soil for sufficient depth below the bottom of the excavation. Now, though these sheet piles come in many cross-sectional profiles, the most common is the Z section. This is the one that you see here. These sections are driven into the ground one by one using either hydraulic hammers or vibrators. For deeper excavations, I'm talking about greater than 15 feet or so, sheet piles are braced with horizontal or inclined braces, or they're anchored with tiebacks. We'll talk about those in a minute. What we see here is a steel sheet pile being driven into the ground with a diesel pile driver. This system shows us various bracing techniques for our sheet piling. System A and B listed here are simply whaler brackets placed horizontally and vertically. But System C is what's called a tieback system. I'd like to take a moment and take a closer look at the tieback system. What you're looking at here is a section through an excavation, which is supported by soldier piles and lagging. We'll talk about what those are in a moment. Tiebacks are installed as the excavation proceeds. This is followed by the bolting of the lagging to the soldier piles. However, the number of tiebacks required is going to be a function of the depth of the excavation as well as the type of soil. Now, as the excavation proceeds, we're going to drill holes right through the soldier piles. After the tieback hole has been drilled, high-strength steel tendons are placed inside the hole, and then the hole is pressurized with grouted high-slump concrete. Once that concrete reaches sufficient strength, we stress the tendon or post-tension it, and then we anchor it straight to the pile. Here we get a shot of a deep excavation. On the left-hand side is the support system, and this is the soldier piles and the lagging. In this case, the lagging is wood, but it can be other materials. The soldier piles are the steel beams that are driven right into the ground, and again, the lagging is the planks, the wood planks, that are bolted to the soldier piles as the excavation proceeds. Here's just a diagram of how the lagging is bolted to the soldier piles. In this case, we have twin C-section soldier piles that are encased in concrete. And then you can see right there, there's a threaded bar which is welded to the soldier pile. And then the lagging, which in this case is pressure-treated lumber, is bolted directly to the pile. Now, in some situations, you're going to have an excavation that is so close to an adjacent building that you can't even use a tieback. In this case, what you're going to use is closely spaced, reinforced concrete piles. These are called Contiguous Board Piles, or CBPs. Each pile is made individually by screwing an auger right into the ground. The auger, which is called a continuous flight auger, has a hollow stem in the middle of it. Now, once the auger reaches the very bottom of where the pile is going to be, what they do is they take a high slump concrete, and this is pumped down the hollow stem of the auger to the bottom of the bore. Once the pumping starts, the auger progressively is withdrawn from the hole. The withdrawing auger brings the soil from the bore to the surface, where it is removed. Thus, the sides of the bore are supported at all times from the soil filling the auger or by the concrete. Immediately after the entire bore has been concreted, a reinforced cage is lowered into the concrete-filled bore. Now here's a shot of a deep excavation in a very congested area. As you can see, in kind of the upper left-hand corner, there is an adjacent building, and right below that, kind of in the middle of the photo, they use contiguous concrete piles. But as we move away from that building, you can see that they've switched back to soldier beams and lagging. That's because here in the lower right-hand corner, where there is no adjacent building, they had the room and they could continue on with their excavation. Also, if you take a look at the lower portion of those contiguous piles, you can see that they've been shotcreted. By shotcreting the lower portion, what you do is you reduce the water percolation that can come through the cut face of the earth. Now, as just mentioned, one of the big shortcomings of the contiguous piles is the fact that you wind up with gaps at the bottom, and obviously there will be water penetration because of those gaps. One way to overcome this is by using a modified version of the contiguous piles called secant piles. Secant piles essentially consist of two sets of interlocking contiguous piles. The first set, which is called the primary piles, is bored and then it's concreted in the same way as the contiguous piles. The center-to-center distance between the primary piles is slightly smaller than twice their diameter. After constructing the primary piles, the secondary piles are now bored at a mid-distance in between those primary piles. The secondary piles are now concreted and reinforced in the same way as the contiguous piles. Now, in most situations, only the secondary piles are going to be reinforced. Now, another excavation support system commonly used in situations where you would have a high water table is called slurry wall construction. The slurry is actually bentonite, and the way that it works is you construct two primary panels. These are guide walls, and then you excavate in between them. Now, the thickness of, or the width of these guide walls, one set from the other, is the thickness of the concrete wall that you want to cast. So now, to avoid the trench collapsing in on itself, as you begin your excavation, you continuously fill it with bentonite slurry. Now, bentonite slurry is simply bentonite clay mixed with water. It's made thick enough or heavy enough so that it can retain the weight of the soil that is trying to push in on it. And it pressurizes itself and keeps that soil back. Now, obviously, as we're filling this trench with bentonite slurry, we are trying to also get the soil out. So we have special excavation equipment called a modified clamshell used to extract the material through the slurry. After the excavation for the entire primary panel is complete, a reinforcement cage is then lowered down into the trench. Concrete is placed in the trench panel using usually 2 or more Tremy pipes. Typically, a Tremy pipe is about 8 to 10 inches in diameter, and one will be placed at either end of the panel or perhaps at both ends of the panel. Concrete is placed from the bottom up, and the discharge end of the Tremy pipe is always buried in the concrete. Now, as concreting continues, the slurry is pumped out of the top of the trench and it's stored for later use. Typically, it's pumped directly into a truck. Now, there is a separation system in these, either in the truck or at the plant. Frankly, I don't know which it is, where they separate out the soils, undesirable soils, from the bentonite slurry so that they can reuse the slurry. But as you probably know, this type of concreting takes incredible expertise. The guys that do this are very, very well trained and very, very experienced. Typically, the concrete, especially at the beginning, is a much richer mix. And also, you have to be placing this very, very slowly so that it doesn't get diluted by the slurry inside the wall. What I want to do now is I want to go through this process step by step on the next couple of slides so that you get a bit of feel for how it's done. Now, here what we see are the guide walls. The guide walls are already in place, and the distance from one guide wall to the other is going to be the width of our wall. Now, here what we see are the guide walls. The guide walls are already in place, and the distance from one guide wall to the other is going to be the width of our wall. Now, you may recall I said that you needed special excavation equipment to do this kind of construction. Well, this is it here. This is what's called the modified clamshell, and all that means is that the sides of the clamshell are straight so that it can go straight down into the excavated area, as you see here. And then right above those clamshells, you may see a straight bar. This is called a Kelly bar that is used just to make sure that the clamshell is straight as it begins to excavate in between those two walls. Now here we get a shot of that clamshell up close, digging right through the slurry to get to that area that it wants to excavate. Now, once the entire area has been excavated and filled with slurry, this is just a diagram of that Tremy pipe, which would be driven down to the bottom of the excavated area, and again, the concrete would begin to be pumped out of the Tremy pipe. As it is, the bentonite obviously rises, and as the bentonite rises, it is sucked off the top and pumped back into the trucks. Now here we have a shot of the fabricated steel that is just sitting there, the steel cages, and this is all the reinforcing rods, the rebar, and everything else that is just waiting to be lifted and inserted into the excavated trench. And just to give you an idea of how much steel that is, take a look at this shot. You can see the buildings in the background, and here the crane is picking up the prefabricated steel, getting ready to lower it down into that wall. Another type of excavation support system is called soil nailing. Soil nailing is simply a means of strengthening the soil by putting closely spaced bars along the soil face. So you're driving these nails into the soil and it increases the cohesiveness of the soil, thereby preventing it from caving in. The way that you do this is there's a few steps to it actually, and the first thing that you want to do is you're going to excavate down about 5 to 7 feet at a time, and then you drill the holes along the face. These holes are about every 3 to 4 feet on center on one hole, and it covers approximately 10 to 15 square feet of the cut face. Then the threaded steel bars that are approximately 1 inch in diameter are inserted into the holes, and then the holes are grouted with concrete. At this point, we're going to take welded wire fabric, we place it over the wall of the protruding bars, and then we're going to go ahead and put a layer of shotcrete onto it. Once we do this, plates and washers are inserted onto the protruding bars, locked into place with a nut, and then we put on a second layer of shotcrete. And then the next thing we're going to do is dig down another 5 to 7 feet and repeat the process. And this photo gives us a view of a soil-nailed excavation. Well, as you've already seen, a major portion of doing a deep excavation and deep foundation system is the support along the walls. Now I'd like to discuss the support that is going to be under our building. And here we have, in this presentation, we have two things that I want to discuss. That is piles and piers. We'll start with piles, which are typically made of wood, steel, or concrete. Frankly, I haven't seen too many made of concrete, but they do exist. And these are driven into the ground as opposed to piers, which are cast at the site. There are two types of piles. There's what's called a friction pile. A friction pile is a pile that essentially transfers the load through friction created between the surface of the pile and the soil itself. They are generally tapered on one end, which makes it very narrow, and what this does is it helps the pile driver drive the pile into the ground, but it also increases the friction. There is also what's called a load end-bearing pile, and what this pile does is it simply transfers the load from the building to the lowest strata of the soils. Now again, piles can consist of either steel, it can be made of reinforced concrete, pre-stressed concrete, or wood. Now wood is typically used only where the loads are going to be lighter for a number of reasons. Obviously it's not as strong as steel or concrete, but also wood piles come from tree trunks, and tree trunks just only get to so much of a diameter, whereas steel and concrete we can fabricate to any size we wish. Now how we select our piles and where we're going to use them is going to be a function of several factors. First and foremost is probably going to be availability, and then we also have the cost to deal with, and then the below grade environment. Obviously steel can corrode under certain environments, and concrete, if we're going to be in a soil that has heavy sulfates, we're going to have to use a type 5 cement. And if we have a moderate level of sulfates, then we're going to use a type 2 cement. Now also, because piles are generally smaller in the cross-sectional area, typically piles are not used solo, whereas piers can be. Typically piles are clustered together and then they are finished off with what's called a pile cap, and you can see this in the next slide. And here we see a diagram of a concrete pile cap, which is supported by 3 piles, and typically this is the minimum for a pile cluster. 3, you have to have a minimum of 3 piles underneath a pile cap, and these piles appear to be friction piles, as noted by the tapered end of the pile. And now piers. Piers are often used individually as opposed to piles, which are used in clusters, because with piers we can typically make them at whatever diameter we wish. The typical diameter of a pier is about 18 to 36 inches, but 6-foot diameter piers are by no means unheard of. Another reason that you'd want to use pier instead of a pile is that the vertical alignment of the pier is almost guaranteed because you're the one setting the mold or digging the hole. Whereas with a pile, you're driving it into the ground, and therefore it's not a guaranteed vertical alignment, which is another reason why, especially with single piers, you want to use very light loads. Now when piers are made, they're either designed as a friction pier or an end-bearing pier, or as both. Piers can be made with a straight shaft, or they can be made with a bellied bottom. But a pier generally is reinforced with steel cages before the concreting begins, and when piers are going to be used to support another concrete element, such as a grade beam or a slab, then reinforcing dowels that extend up beyond the top of the pier are going to be placed in there before concreting is completed. And now to just quickly go over the constructing of a concrete pier. The photo on the left here shows a truck with a mounted auger, and that's going to drill the hole for the pier. And then the photo on the right is the reinforcement cage that's going to be lowered down into the hole after the drilling is completed, but before the concrete has been placed. Then here, the photo on the left shows that the concrete is being placed into the pier hole through the chute coming off the concrete truck. And then finally, steel dowels are being placed in the pier just before concreting is finished. Now, if this pier were to be going to be supporting a wood or a steel column, for instance, then steel anchor bolts would have been used in place of these dowels. And finally, last couple of slides here. We cannot talk about foundation work, whether it be shallow foundations or deep foundations, without talking about the battle against groundwater. Groundwater is going to be an issue when you are doing foundation work, and two of the best ways to remove groundwater are either through sump systems or Wellpont systems. Now, sump pumps or sump pits is something that all of us, I'm sure, have encountered at one point or another. Probably have used them in our basement if we're unlucky enough to have our basement flood from time to time, as I have. So the way that this works is simply you create a pit within the enclosure of the excavation. The bottom of the sump must be sufficiently below the final elevation of the excavation. Then as the groundwater percolates in from the soil, the sump just grabs it, pumps it out, and discharges it to an appropriate location. Now, a sump pump is going to work fine where we have a cohesive soil and the percolation rate of the water coming into your excavated area is very slow. However, a more effective dewatering method uses forced suction to extract the groundwater. This works by sinking a number of vertical pipes with a screened end into the bottom of the ground. These areas are called well points, and you put these well points around the perimeter of your excavation. The well point reaches well below the floor of the excavation, and they're connected to a large diameter horizontal pipe, which is known as a header. The header pipe is connected to a vacuum-assisted centrifugal pump that sucks the water out and discharges it to an appropriate location. Now in the next slide, you're going to see what happens when you don't have a good dewatering system. So go ahead and take a look.
So as we see this poor fella try to dewater his excavated area, this is going to conclude week 4 of horizontal construction, and I'll see you all next week in class.